In this module we will be looking at solution of Helmholtz equation. Okay. We have defined what is Helmholtz equation. It is actually the one that does not contain explicit time dependence. Okay. So we want to find out how to solve this Helmholtz equation. It generally turns out that it is actually very difficult to solve this Helmholtz equation, but it is possible to pick certain, based on some intuition, it is possible to pick certain directions for the electric field, okay, and then see if our picked solutions or our guessed solutions are actually consistent or not. Okay. Let us imagine that these waves, electromagnetic waves, are being generated by some action at sun, okay, which we can assume to be very, very far away from us, right. And let us also assume that these waves are of a particular frequency only, although this may not be true, and it is not true in fact in general, but let us assume for simplicity that these waves which are generated on sun are of a particular frequency. So these waves are coming to us, okay. The waves are actually spherical, okay. This is, we are not going to prove that one here, we can prove that one later, but the waves which are generated are all spherical, and then they would start expanding like this. You must have seen many movies, or you must have seen it if when you drop a pebble in the pond, that there would be this expansion of spherical surfaces. So these surfaces expand like this, but by the time they reach earth, the expansion would be so large that over the entire earth, or at least over the region that I am considering, let us say I put up my receiving antenna over here to intercept the sun's rays, then over this antenna, which could be say 1 meter by 1 meter for example, that wave which is coming, although is spherical, becomes locally like a plane wave, right. See, it is like, imagine a ball, okay. So you imagine a ball, and then imagine the radius of the ball being increasing, and then you start to pick of a very small region of the ball, okay. And if you see that region, that looks almost like a plane of paper. Rather than a curved surface, it looks almost like a piece of plain paper, right. So this is the sphere that I have, okay. And then if I now pick up a very small region, which is what would happen, right. See, this is the small region. Why? Because this spherical surface which represents the wave generated from sun is actually quite large, right. So and on that I am putting my small receiving antenna and saying what is the variation of electromagnetic field over here on this antenna. So this is a small region which I am seeing. So although I would be looking at a curved surface like this, right. So this is the curved surface that I am looking at, but for all practical purposes, right, this can actually be replaced by a plane graph, okay. So these kind of waves are called as plane waves, okay, and we will be looking at plane waves, okay. And mathematically plane waves are quite easy to specify, because they can be specified easily. I will tell you in a minute now, but physically plane waves cannot really exist, okay, because mathematical plane waves cannot exist simply because you will see why they cannot exist. But the idea is that if a wave source is sufficiently far away from the place where you are looking for the waves, then you can actually model that wave as a plane wave, okay. So that is the whole idea of using plane waves. This is why sometimes this is called as plane wave approximation, and that is very widely used in electromagnetic studies and optical studies, okay. So how do we define mathematical plane waves? Mathematical plane waves can be defined by writing, so mathematically plane waves can be defined by associating E and H fields to be of this form. Which form? I will just, in a minute I will draw that. The form is this. These are the electric field lines, okay. these are the electric field lines of the plane wave, okay, and these are the magnetic field lines. You can see that these electric and magnetic field lines are all crossing at right angles. So you can see that these are all crossing at right angles, okay. Okay. So this is like taking a wired mesh and then putting it up in front of you with one axis pointing to the electric fields. This is the electric field and this is the magnetic field, E and H fields, okay. So these are called the plane waves, and these plane waves have to be advancing, they have to be propagating somewhere, right. So if you go back to this spherical wave, you know, which is expanding like this, spherical wave expanding like this, right, it actually means that I have these plane waves, right, which are expanding all the way, right. So these plane waves are all expanding all the way over here, right, and then this is how the plane waves are expanding. So if I consider the direction in which these plane waves are expanding as z axis, right, okay, let me consider the direction of expansion of the surface of wave surface as z axis, then it is immediately clear that electric field and magnetic field both have to be in plane that is perpendicular to z axis, correct. They have to be plane that is perpendicular to z axis. So for example, if this is my axis of propagation, the wave is propagating like this, and this is my magnetic fields, okay, or you can think of this board that is there at the back here, okay, as consisting of lines which are electric and magnetic field lines, okay, and then the board is advancing towards you, the board is coming towards you in the z direction. So this is the direction of wave propagation, and these are the electric and magnetic fields, okay. So we are free to choose electric and magnetic fields to be lying along x or y direction, but they have to lie only in x and y direction, and they have to be perpendicular to each other, and they have to be perpendicular to the plane that contains both, right. So E is perpendicular to H, which is perpendicular to z axis, which is the direction of propagation. This is the first rule for a plane wave which is propagating along z direction. If the plane wave direction is considered to be x axis, then E and H must be perpendicular to each other, and they have to be perpendicular to x axis. In that case, electric and magnetic fields will lie in yz plane, okay. So that's as simple as that. So you have electric fields and magnetic fields now in xy plane and perpendicular to z axis. Now within this xy plane, can the strength of electric field vary? We can rigorously show that the strength of electric field and magnetic field cannot vary, they have to remain constant. This is a plane wave, the strength of electric field and magnetic field remains constant in xy plane or completely independent of xy coordinates. You can kind of intuitively think about why this is so. If they were to actually depend on x and y, then there would be some curl, right, and there would be some divergence. But if there is divergence, then del dot E will not be equal to 0, right, and del dot B is not equal to 0. Therefore you cannot have variations, okay. We will not prove them rigorously, it's not important, but take this point that electric and magnetic fields must be independent of x and y coordinates. These conditions are sufficient for us to consider electric field, magnetic field and z axis as a system of three mutually perpendicular axis, right. So one electric field, magnetic field, and when you turn electric field, magnetic field, it would propagate in the direction of z axis. Now you might rightfully ask, who stopped you from considering propagation along minus z direction? Answer is no one. Actually, there could be exactly a wave which is going along minus z direction also, because the equations actually don't tell you that you have to consider only forward propagating equations. They also tell you that you can consider, in fact mathematically, the solution would be backward propagating or negative z propagating solutions as well. Okay, and if you go to that, electric field and magnetic field should be in such a way that electric field to magnetic field will point in the direction of z, then you have to appropriately change the electric field and magnetic field orientations. Okay, other than that, there is no problem if you consider negatively propagating wave equation, wave solutions or waves. But of course, physically you might not have a source, right? See, if only there is a source on to the right side, there would be some waves which are going in backward direction. If the source are on the left side and you consider this as the right side or the z positive z axis, the waves would only propagate to the forward axis, to the forward z region. Okay, if there are some reflectors or scatterers in between, then it is possible that at any given region of space there could be propagation of both plus z and minus z waves, and those are some examples that we will see later. Okay, so to recapitulate, the solution for Helmholtz equation is in general complicated. To simplify this complication, we will assume a plane wave approximation. Plane wave approximation is very nice, very valid approximation when the source of waves are quite far away from the region where you are talking about this. Mathematically, plane waves can be defined by associating electric and magnetic fields such that they are both perpendicular to the direction of propagation, say z axis, okay, and they remain constant in the xy plane, or they remain independent of xy coordinates. So effectively what I have now is electric field being consisting only of, say, x component, which is x hat Ex, right, and it should be independent of x and y. So what can it be dependent on? Only z. Yes, only when you keep moving far away from the plane wave, then its amplitude might change, amplitude would decrease, right? Otherwise the amplitude is independent as long as you are at a constant z plane. Okay, so this is the expression for electric field. Now similarly, magnetic field has to be along y hy of z. Now let us see whether whatever we have used some physical justification and intuition actually is also mathematically valid. Can we show that these assumed solutions are actually solutions? If they are, what is the nature of this Ex of z and Hy of z? Okay, so to do that, let us recall Helmholtz equation, that is del square plus omega square by v square into E is equal to 0, and instead of writing omega square by v square every time, let me introduce an expression, okay, which is a constant k, which is equal to in which such that k square is equal to omega square by v square. Okay, so let me introduce that so that this equation becomes del square plus k square, okay, into E is equal to 0. Now expand this equation. What is del square? Del square is del square by del x square, del square by del y square plus del square by del z square. Electric field E. Electric field E is nothing but x hat Ex of z, right, plus k square, there is x hat Ex of z is equal to 0. Correct? Now Ex is only function of z, it is not a function of x or y. So there is no point retaining this del square by del x square and del square by del y square terms. They all cancel each other, and then there is x hat everywhere, so which simply means that I can drop the vector also from this condition and then just replace this with a scalar equation, and I get del square Ex by del z square plus k square Ex is equal to 0, right? And since Ex is only function of z, there is no need for me to write down this as del square by del z square. I can simply write this as d square Ex by dz square. Okay. This is the equation that is highly simplified from Helmholtz equation, okay, based on our ideas that we have discussed previously, and we want to see what is the solution for electric field Ex. How do we solve this equation? Well, I do hope that you remember your solutions for differential equations. So the solution that we were looking for was for this equation, d square Ex by dz square plus k square Ex equal to 0. The solution of that equation is have d square Ex by dz square is equal to minus k square Ex, correct. The solution for this would be Ex of z is equal to some constant a e to the power j k z plus some constant b e to the power minus j k z. Does it actually satisfy this equation? Can you just verify that this is actually the equation? I leave this as an exercise to you. Okay, this is a small exercise to you to show that this assumed solution or this guessed solution indeed satisfies original equation, okay, which is this one. We'll call this as some equation 1, okay, equation 1. You should verify that. For example, you turn off b, okay, then what would happen? You have a e power j k z. So differentiating once with respect to z, you will get j k, twice you will get j k square. J k square is minus k square. So minus k square into Ex is equal to minus k square into Ex. Therefore, this is a solution. Similarly, minus jk would also be the solution. So it's up to you now to whether retain a plus kz solution or a minus kz solution. Mathematically both exist, but if you now say that, well, you know, I don't have any wave, any physical source which would actually push the waves along minus z direction, then I can make this equal to 0, okay. If not, then I don't have to make it equal to 0. So this is called as the forward wave and this is called as the backward wave. I am using forward and backward in an analogy with transmission line, which we are going to study after the wave modules, okay. Based on that, any wave which is going along positive z direction is forward wave for me, any wave which is going along minus z direction is called backward wave for me, okay. So that's just my simple short notation that I am going to use, okay. I have Ex of z is equal to, considering only the forward wave solution, I have Ex of z is equal to a, which is some constant, and instead of talking about a which conveys no intuition, let's call this as E0, okay. E0 stands for some amplitude of the electric field. So you have E0 e power j k z as the solution. Do you recognize what has actually happened over here? The expression for electric field is depending on z, correct, but it is actually a complex number, right. If you try to sketch this one, you will not be able to sketch this. It would actually be a complex number. You will have to sketch the real part first, sketch the imaginary part first, right, or you can interpret this as a phasor, right. So if you actually think of this in terms of the phasor with real and imaginary axis, then this corresponds to a phasor which is rotating, right, with an angular velocity of kz. So you fix z and fix k, then it would point to a particular direction, but if you keep moving along z, then this would actually be a phasor which is rotating, okay. Are we also satisfied that its amplitude is changing only with z? Yes, because there is no change in x and y directions, right. So this is just a wave which is propagating along z direction, right. The second thing that you have to notice is that this is a phasor one, therefore then it is not the complete time dependent form, right. So if you want to find the time dependent form, you have to multiply this Ex of z by e power j omega t, then take the real part of it, right. So to obtain the time dependent form, which is Ex of zt, and what do you get if you do this operation, multiply by e power j omega t, you will get e power j omega t into e power j omega t plus kz, okay. And with that, if you go back here, you have electric field here as real part of Ex of z, and substitute for Ex of z here, I get E0 e power j omega t minus kz, and real part of this is nothing but E0 is real, therefore E0 comes out of the real operation. You have E0 cos of omega t minus kz. This is the expression for electric field. Okay, this is in the scalar form. If you want to write down the expression of the electric field in the vector form, you can attach the appropriate vector direction, right. So this electric field would always be directed along the x-axis, and if you were to fix z and t and everything, this cos term is fixed, then it would point with an amplitude of E0 times something, whatever the cos value is, something, and it would always point along x. Okay. There are two things we can do now. Fix t and see what happens with respect to z, and fix z and see what happens with respect to time. This is like I take an oscilloscope, I hook it up into air, okay, and this oscilloscope display should tell you the electric field, okay, that of the form cos omega t minus kz. And I am not satisfied with only one oscilloscope at this particular point in z. I have 2-3 different oscilloscopes, okay, kept at 2 different or 3 different points along z direction, okay. Now if I were to say this is z equal to 0, okay, and this is z equal to something, this is z equal to something, rather than talking about z, it's easier for me to talk in terms of kz, okay. So kz equal to 0, kz equals pi by 2, kz equals pi. I have got 3 different oscilloscopes at values of kz equals 0, kz equals pi by 2, and kz equals pi. This kz equal to 0 is my reference, okay. Now with that, if I were to see what is the display on the oscilloscope, right, what would be the display that I would see? Go back to the expression, take kz is equal to 0. With kz equal to 0, the expression for electric field will be x hat E0 cos of omega t. So if you were to look at the oscilloscope display, you would actually see a display that would look like this, correct. This is the cosine waveform, this is a time, so this is the axis with respect to time, so this is a time t equal to 0 with an amplitude of E0, right. This will have an amplitude of E0 and it would go as in this particular fashion, okay. Now if you try what happens at kz is equal to pi by 2, you get x hat E0 cos of omega t minus pi by 2. Now cos of omega t minus pi by 2 is sin omega t, right. So this would be cos omega t minus, so it would be cos omega t cos pi by 2, which is 0, minus, sorry, plus sin omega t sin pi by 2. So this would actually be equal to x hat E0 sin omega t, right. So you look at your oscilloscope display, the oscilloscope display would now show here, right, a sine wave at time t equal to 0 with the maximum amplitude of E0 again. But if you notice at kz equal to 0 and kz equal to pi by 2, you will actually see a pi by 2 phase difference, right. This wave at kz equal to pi by 2 is actually lagging the first wave by a value of pi by 2, right. Similarly, now when you try kz is equal to pi, what you get is x hat E0 cos of omega t minus pi, right, and this is cos omega t cos pi, sine will anyway be 0. So this would be minus x hat E0 cos omega t. So if you look at the oscilloscope display will show you a wave that would look like this, correct, with an amplitude initially at t equal to 0 as minus E0, right. So you can actually see that if you were to put a point of reference, some small object over here, right, this small object as you see is at different times, appearing at different times, right? You don't have to do this one with respect to time. You could actually fix time. Okay.